welcome to our lecture, Chapter 10. We're going to be talking about the Ancova, otherwise known as the analysis of covariance. So we first need to ask, what is analysis of covariance? We already studied what an analysis of variance is, so this is an extension of analysis of variance. However, there's a couple other statistical analysis involved in this process which has not been discussed, one having to do with linear regression, which is in the next chapter, and then the next couple chapters, and then also correlational analysis, which is in the very next chapter. So let's really look at its definition, its general definition, then we'll talk about some applications when it would be appropriate to use the analysis of covariance. So like I said, it is similar to the ANOVA, but it's used to assess differences in the means of at least 2 or 3 or more groups as defined by the independent variable. So just like the ANOVA, it runs very similar. However, there's one aspect that needs to be, or that is added when you're looking at the Ancova, and we're looking at a extraneous variable or another variable that we want to control for when looking at the results, and this variable is called the covariate. So in this instance, they're saying the covariate might influence a relationship between the dependent variables. So we're looking at the output of 3 or more groups, and we're saying, well, this continuous variable may affect the differences we need to control for it statistically. It's a statistical procedure, control technique. It's not a design control technique like manipulation, elimination, or inclusion, where you might see in an experimental design. Statistically, we'll control for it. And this is, of course, best understood through examples. So the general idea is that when you control for this covariate, or remove it from the equation, more or less you're not fully removing it, but you're just factoring in the differences and controlling for what they call the error variance. So you're reducing the error variance, and it's always going to increase statistical power when you control for that variable. And if we remember our definition of power, it's a likelihood of correctly rejecting the null hypothesis. Okay? So the second point here is interesting. It says adjust associations for other continuous variables that could be alternate explanations for the association. So they're using this word association. We haven't talked about this too much, particularly because we have not gotten into the correlational analysis. The term association, again, is one of those technical terms that is used. It's synonymous with the word correlation or relationship. Okay, so to adjust the relationships for other continuous variables. So in other words, it's saying there is a relationship or correlation between the continuous variable and the dependent variable, and this must be known before you run your analysis. It's kind of like an a priori thing. How would you know that? Well, study of the literature would probably tip you off that one specific variable would affect the outcome. So let's control for it. And this is done usually from a deeper understanding of the literature. So here our hypotheses are, there's no difference in the means between the 2 groups. I shouldn't say 2, but multiple groups after controlling for the covariate. And then, of course, our alternate would be there are differences after controlling for the covariate. So what type of research questions will we utilize for the Ancova? Just before we talk about this one of the most reasonable research scenarios that you would include a Ancova if you're looking at experimental designs. Sometimes I represented these as diagrams in other presentations, but just think about the basic pre-test, post-test design, where one group is exposed to the treatment, and then let's say your second group is a control group or attention control, either way, and they each have a pre-test, and then their post-test follow the intervention. The Ancova would be the appropriate analysis for that, assuming we randomly assigned participants to one of the two conditions. The differences in the pre-test would be balanced out or quote-unquote controlled for through the Ancova, and then the differences in the post-test would then be analyzed. So you can imagine, even though random assignment to each of the conditions, the control group would have a pre-test mean, and the treatment group would have a pre-test mean, and they may look a little different. So the differences in the post-test would even thus be more different, and that's what your error variance would be. So let's control for the differences in the pre-test between the two groups using an analysis of covariance, kind of balance that out, so to speak, and then we'll be looking at the post-test differences on the even playing field. There's non-experimental scenarios where you can look at observational data as well, and we can talk about those examples. Here we have a different type of research scenario, and we can look at the effect of exercise on bone mineral density. So let's say our independent variable here is exercise, and then our outcome, our dependent variable, would be bone mineral density. That's otherwise known as a measure of bone strength. Okay, but so we have our IV exercise, okay, and then we have our DV bone mineral density. Okay, but there's another variable out there. Okay, it's an extraneous variable, and we know it will affect bone mineral density, and that has to do with diet. Okay, so we have that extraneous variable diet, and we're not controlling for it through some type of design control where we make sure all our participants eat certain types of meals. So we have to statistically control for it by entering diet into the equation as a covariate. Okay, and how do we know diet affects bone mineral density? Like I said, this is through an understanding of the literature that there is a relationship between diet and BMD. We know that, but we're also going to test for it statistically in our analysis just to prove or confirm that the relationship or correlation does exist. Okay, so our question is, how can we tell if exercise has an independent effect on BMD when controlling for diet? Okay, so we're going to use the following questions. What is the effect of regular exercise on BMD once the consumption of fruits and vegetables are controlled for? So that is data that we would have to collect or have to have access to, so we would have to know that so we could enter it into the equation. Of course, our dependent variable would be BMD. Our independent variable, broken down into two different factors. We would have regular exercise for two groups, 0 to 2 times a week, and 3 times or more a week. And then our covariate would be the number of portions of fruit and vegetables consumed daily. Okay, and let's look at the type of data. Our dependent variable would always have to be continuous, particularly because Ancova is a parametric technique. The independent variable is categorical, so the categories of exercise, either you're in this exercise or that exercise group. And of course, covariate is continuous amounts of fruit or produce consumed. Then our assumptions for Ancova, a little bit different than Anova. Some of them are the same, but there are others that must be added because of the other types of analyses that are involved. The groups defined by the independent variables are mutually exclusive, so we always have that independence assumption, and that's pretty much the same for all parametric analyses. The equal variances amongst the groups are between, or with, and that's our homogeneity of variance. The dependent variable is normally distributed, hence the use of the parametric equation. And the covariate and dependent variables have to have a linear relationship. So we would assume that as The covariate in this instance was fruit or consumption of fruits, and our dependent variable is bone mineral density. So if it's going to be linear, that means basically as one variable goes up, the covariate, for example, as that increases in number, then the bone mineral density would also increase. So linearly, as one increases, the other increases, and it follows that straight line. Or as one decreases, the other decreases. Okay, and it continues that trend throughout infinity. I know that's kind of hard to imagine, but that's the mathematical precepts underlying this, okay? So similar direction and strength of the relationship between the covariate and the dependent variable. This one, again, may be a little bit hard to understand because we haven't studied correlations yet. The definition of a correlation is that it measures the strength and direction of the relationship between two variables. So in this case, our covariate is consumption of produce. Our dependent variable is bone mineral density, BMD. So the direction would be positive. So as one increases, so does the other. If it were inverse or negative, that would mean that as one variable increases, the other decreases. And then the strength has to do with how strong is the relationship between the two. So does it really strongly affect or not? Is it more or less weak? So that's really what the correlation gives us, strength and direction. So we go through our 6-step process. We'll state the hypotheses, define the significance level. Usually when you're in SPSS, it gives you the default by 0.05. We're going to make sure the data meet all the necessary assumptions, like homogeneity variance, linearity. In this case, did I say homogeneity variance is it's that the data must be normally distributed, so on and so forth. We're going to obtain the means, standard deviations. These are descriptives. We'll compute the test statistics, and then we'll look at the significance, determine whether or not the results did happen by chance or not. So we'll illustrate the Ancova with the following question. It's a level of exercise related to bone mineral density in a group of healthy community-dwelling women. Once fruit and vegetable intake is controlled for. And so we'll answer this question. We'll use data from 50 women. The dependent variable, BMD, independent variable, defines the groups, exercise 0 to 2 times per week or 3 or more times, and then the covariate in this instance was the number of servings of produce that they consume. So let's state our hypothesis. Mean bone mineral density in the two exercise groups, they do not differ when controlling for consumption, and the alternate is just opposite, basically saying that they will differ. Okay, so here what we say is a statistically significant difference between the means exists. The p-value of the computed F statistic must exceed the critical value. And again, the critical value is automatically entered into the equation in SPSS. You wouldn't do this type of analysis by hand. It would just be a little bit too difficult and completely not necessary. And then the alpha level is always going to be at 0.05 by default. And like I said, using SPSS, that's what it uses it. So let's first look at the assumptions and make sure that they are met. So remember, like I said, one of the assumptions had to be with the association, otherwise known as relationship, otherwise tested statistically through correlational analysis. The little r there is a statistical symbol for correlation. So what we're basically saying is that there is a relationship between our two variables, our covariate and our dependent variable. Our covariate was consumption of produce, and dependent variable is BMD. The correlation is 0.5, which is pretty strong because correlations go from 0 to 1. It's almost a 0.6, and it's significant, basically saying that those results didn't happen by chance, and that So in other words, it is a linear relationship. So as one variable increases, as produce intake increases, so does B and D. And it looks pretty strong, and our results say this did not happen by chance. So we're just confirming that there is a relationship or association. It is positive and it is rather strong, so strength and direction. Okay, the strength and direction of the relationship are confirmed, and we confirm that it is a positive, and we confirm that it is indeed a covariate and should be controlled for. Okay. The next thing says, since the interaction term is not significant, we determine that there is no covariate group interaction and that the effect of the covariate is similar across different groups. So basically, what that means is if you look on the left-hand model, exercise, star, produce, that's looking at the interaction. So is there a difference when looking at the two groups? Does it matter whether you exercise 0 to 2 times per week or 3 times or more? Is there some kind of effect or interaction? And basically what this is saying is no. It doesn't matter whether you're exercising 0 to 2 times or 3 or more times. There's no interaction. So that's important to understand that. Okay, so the next assumption, we want to check the variances between all the groups. And again, we always want this to be non-significant, assuming that there is variances between those groups. Okay, so this is a Levine's statistic, and we want it to be non-significant. Okay, and then it always gives you the little highlight down at the bottom, test null hypothesis, that the error variance of the dependent variable is equal across all groups. Okay, so let's look at our means. The means estimated from the Ancova procedure are adjusted for produce consumption. So this is the adjusted means. All right, so this shows what the difference in the means of the two groups would be if produce consumption were equal in the two groups, and we know that they're not, but although we statistically manipulated the data and balanced it out. Okay. So here we want to go ahead and evaluate the tested statistic, and we can see that there's a significant difference between the bone mineral density by exercise group, and it's at 0.023. So if we look at the exercise under the source, the left-hand column, and we can look straight across the F values of 5.3, and our significance is 0.02, which is less than 0.05. In other words, the differences did not happen by chance. Okay. So we can say after adjusting for the produce consumption, so we adjusted and made it all even, and so there won't be any differences. The mean bone mineral density among women who exercise less than 3 times a week is 0.76, okay, and among women who do exercise more than 3 times is 0.88. Okay, so this difference in the mean bone mineral density after adjusting statistically significant, and so in other words, the results did not happen by chance. Okay. So this ends the presentation for the analysis of covariance.